night, and we are doing pre-calculus here on YouTube Live. I'm very excited to have Steve Kokoska and Tom Dick and Vicky Carter all together here this evening to give you their expertise on the content of this AP pre-calculus course, and really just pre-calculus in general, and some great TI tips on the graphing calculators and ways to explore that content. So very excited for this evening and the content. A couple of housekeeping things. One, this is our last pre-calculus live event of the year. This year we'll be back in January with a schedule. At some point during this session, I'll post the date and time of that first session here in the chat box so you guys can see that. And then the other housekeeping bit is if you have not already downloaded the student document to go along with tonight's session and you'd like to follow along with some of the questions, that link is down in the description of this session. If you just click the little more box there in YouTube, you should be able to get that link. Otherwise, I'll post it here in the chat in a moment. Steve, I think you're taking it away from here, so I will
Thank
let
you.
you take it.
All right. Thank you, Curtis. Great to be with you and Vicky and Tom again this evening. We've actually got a couple of things we want to try tonight. We did not have the opportunity to look at question number 2 way back in August. So we're going to start by looking at question 2, one of the free response questions from the 2025 exam. This has just a little bit of regression in it. That's the topic actually for tonight, but it has some interesting calculator applications that we felt obligated to talk about. And if and when we get through this one, we'll get to another problem specifically about regression and some of the regression diagnostics that students are expected to know. Now, this document, Curtis, that we have up here first, this one is not available through me or through TI. This is actually on AP Central. I don't feel comfortable, posting these scoring guidelines separately, but people can get a hold of this on AP Central. Now, we've added a little bit more, and you can take a look at that in the recording, but this document basically is on AP Central. So, all right, I'm going to start taking a look at question number 2, and Tom and Vicky are going to chime in, and Tom's going to do some calculator work, and Vicky's going to correct me as I make some errors here. So here we go. This is this problem is about a musician who's posted a song on a streaming service, and he decides to count the number of times that his song is played. I would think of counting the number of times the song is downloaded, but okay, this is fine. So actually, the way that you read this is the song is available on the streaming service, but then all of a sudden, a couple of months into this, he decides, oh, I'm going to count the number of times that this song has been played. So t equals 0 is not the very first instant that this song has become available. It's the time at which this musician is counting. So there's a table of values given here. T equals 0 is when he starts counting. And the song has been played 25,000 times. Notice these values are given in thousands. The time t equal 2, I think that's 2 months. And the time t equal 4. Okay, well, the problem, boy, there's a lot of words here. The problem goes on to say the number of plays in thousands for this song can be modeled by this function d, which is given like this. So d is a polynomial of degree 2. It's a quadratic, where d is the total number of plays in thousands. T is the number of months after the musician began to use this app. Okay, so the very first thing we want to do is, whoops, I'm sorry about that. Let's see if we can go back here. We were just talking about how sensitive that is, huh? It says, first of all, use the given data, use the data in the table to write 3 equations that we can use to find the values of A, B, and C in that expression for D, and then darn it, use those equations to find A, B, and C. So before I actually show you the scoring guidelines and how the points were awarded, what I like to do is to give you a solution, how I might solve this. Now, I'm sorry about this, Curtis. This isn't in the exact order that I would do this, but over here to the right is probably the very first thing that I would do. I would notice the D of 0 is just C, and that has to be equal to 25 by using the table. So I know right off the bat that C is equal to 25. Now I can get two other equations here by letting T be equal to 2 and T equal to 4. So I plug those into this equation. And I get 4A plus 2B plus C is equal to 30,000 after 2 months. And 16A plus 4B plus C is 34 after 4 months. Now, I know that C is equal to 25, so I'm going to let C be equal to 25, and I'm going to simplify those two equations. So in my class, I like to talk about this as a system of two equations and two unknowns. And so I ought to be able to solve this one. Now, there are many different approaches. Here is a way to do this. I notice that if I multiply the top equation by 4, multiply the left-hand side, the right-hand side by 4, these two terms will be exactly the same. That's a good thing. So I multiply the top equation by 4, and then what I'm going to do is subtract the bottom equation from the top on the left-hand side of the equal sign and on the right-hand side. Well, the 16a's will cancel. 8b minus 4b is 4b, and 20 minus 9 is 11. And therefore, I can solve for b and get an 11/4. Now, for whatever reason, and we were talking about this a little bit before we came on the air, for whatever reason, this problem asks for these answers as decimal approximations. So I have to convert that to a decimal. I can think a little bit about this. It's not bad because the denominator is 4 there. So this is 2.75. Now, how do I get the final value, A? How do I get that one? Well, I can go back here to any one of these equations, this one or this one, and substitute in that value for B. I think I used the top one. And solving for A, I eventually got a minus 1/8, which in decimals is a minus 0.125. Now, again, this is a calculator active question. And so I guess the exam, the people who made up this exam were expecting students to perhaps go to their calculator to get this decimal approximation, not sure. And then just to sort of complete this for my own benefit, I wrote this expression for D down at the bottom. There it is. There's that second degree polynomial. I'm ready to go. I think I've done everything I can here for part A. Now, Tom and Vicky know I like to use the TI-Nspire, so I'm going to show you some cool things I think on the TI-Nspire. This calculator will actually let you solve a system of equations. So I can solve a system of 3 equations and 3 unknowns. So it's kind of hard to see up here in this top line, but I've input the system of 3 equations within curly brackets or curly braces. And you can see that the very first equation I have is C equal 25 because, well, I got that from letting T be equal to 0. And then you can see the other 2 equations there that I had on the previous screen. And then after that, I have to tell the calculator, well, what do you want to solve for? So I have to tell it A, B, and C. And this comes back immediately and tells me there are the values for A, B, and C. That's really cool. But then I thought about this a little bit. I said, hey, well, wait a minute. This asked me for a decimal approximation. And so I guess a way to do that is to make one of these values up here in this line a decimal, or I can just say, multiply the whole thing by 1 point. There's my decimal approximation. Now, this is also really cool on the Nspire. Look at this one. And this is a question maybe here, Curtis, will have for people on the air. So what I did in the TI-Nspire is I created a list and spreadsheet page, and I input the months in one column and the plays in the other one. And then on my left-hand screen over here, I was able to construct first a scatter plot of just these 3 points. And then I was actually able to construct a regression equation a polynomial regression equation of degree 2. And son of a gun, that's the exact answer. So the question is, why does that regression equation come out to be this exact quadratic that I'm after? That almost doesn't seem quite right. We'll leave that as sort of an open question here. Cool. It seems like the TI-Nspire was almost built for statistics. Those actions are very easy to do, to input a couple of lists of numbers, to quickly construct a scatter plot, and to very easily get a regression equation. I hope I have the opportunity to get the problem number 2 this evening because there's some nice stuff there with the Nspire also. Okay, so here's the scoring guidelines. Here are the scoring guidelines for this part A. This was worth 2 points. The first point was for evidence of the 3 equations, and the second point was for the 3 values A, B, and C. On the left-hand side here, you can see what was presented in the scoring guidelines. I think I had all 3 of these equations. I didn't write them nice and neatly one under the other, but I think I had all 3 of them. And you'll notice that on the scoring guidelines, they solve these sort of, well, analytically or by hand, but indeed they do have the decimal approximation. So 1 point for the equations, the setup, and 1 point for the values A, B, and C. There are some general notes here. I won't go through all of these up at the very top here, the general scoring notes for question number 2. A lot of this has to do with decimal presentation errors. Remember that when students are asked to present an answer, with decimals, they have to present 3 digits to the right of the decimal, rounded or truncated. Sometimes students make a decimal presentation error. That is, there are 3 digits required, but they might only give us 1 or 2. If they do, that's considered a decimal presentation error. They don't earn a point at that part of the exam, but they will not be docked if they make that similar or a decimal presentation error further down the line in that problem. So let's see, I'm going to take a quick look over here if I can, Curtis, scoring notes for part A. The first point is earned for presenting the 3 equations. Yep, we got that. The second point is earned for the correct values. This is interesting. I underlined this, with or without supporting work. So this is kind of interesting. This is a calculator active problem. So as long as the student presents the correct mathematical setup, that is the 3 equations and 3 unknowns, they could then go directly to their calculator and write down the values for A, B, and C. So they don't have to present any supporting work evidence of how they got those values. This one here you can spend a little bit of time thinking about, but some students, of course, did everything in thousands. And those sort of responses are still eligible to earn both points, but there's got to be some, I think, consistency there.
And Steve,
Yes, please.
while we're on that bullet point, I would strongly urge students not to go into those making these numbers into thousands.
Oh, I
I think
agree.
they get very awkward. They may
Yep.
accidentally leave a 0 off. And so anytime you see any question that's worded in terms of thousands of, in this case, downloads, just keep that in the back of your mind and realize that each number that you're using is in thousands. So
down at the bottom of this page, there's a little bit about partial credit, and I'm not going to go through that with you, but I do want to remind you that this is something that's kind of unique to pre-calculus, where they are trying to give credit for good pre-calculus work. And so they recognize that a student may not get all of the first point, they may not get all of the second point, but they've done enough to earn 1 point in some way. And so there are these sets of rules that often allow graders, to award students partial credit. All right, very good. Let's take a look at part B. Is that all right, Tom? Can I continue here?
Sure, Steve.
Okay. All right, good. So in part B, we want to use the given data to find the average rate of change of the total number of plays for the song from t equals 0 to t equals 4 months. And again, it says express this in decimal form. Well, okay, we know this formula for the average rate of change, d of 4 minus d of 0 divided by 4 minus 0. I need to go to the table in order to find d of 4 and d of 0. I did a little bit of subtraction, a little bit of simplification. I got 9/4, but then I remembered this has to be expressed as a decimal, so I've got a 2.25 there. It's important for students, I think, to do a couple of things. Make sure that you show a difference, make sure that you show a quotient. And I would also suggest that you do not go directly from here to the answer. Often what readers, graders want to see is that you are able to get the exact value from the table, that you read the right, correct value from the table. So don't forget to include these intermediate steps, or at least one of them anyway. All right, use the average rate of change to estimate the total number of plays for the songs at t equal 1.5. There are a couple of ways to do this. First of all, I know that the slope through these 2 points is 2.25. I found that up in part I. I can use either one of these points in order to find the equation of that quote-unquote secant line. So here's sort of the general form of this. Well, okay, sorry, we're using a t here. So y minus 25 is equal to 2.25 times t minus 0. So I did a little bit of simplification, and there's my equation of the line. Do you have to put it in that form? No, not necessarily, unless it's asked for specifically. But it seemed to me that might have been a good thing to do, or an easy thing to do here, especially since this value was 0. And now I need an estimate when t is equal to 1.5, so I simply plug 1.5 in there. Probably used my calculator for this just to double check. And I got a 28.375. Beautiful. So those are my solutions. Here's the model solution up at the top. 1 point for the average rate of change and 1 point for that estimate. What is the estimate at t equal to 1.5? That seems very reasonable, seems logical. This is interesting here that in the scoring of this problem, both of these points do require some supporting work. In other words, we can't just see 2.25 and 28.375 on the paper. The student will not receive full credit for that. Those are sometimes called bald answers, answers in which there is supporting work that is expected. The first point is earned for a correct decimal approximation, but there must be a quotient and there must be a difference, as we talked about on the previous page. And yeah, there's another form of the secant line. That's if we use that 0.434. When I was doing this, that just seemed like the more difficult point to use. That's why I used 0 and 25, but the other point is certainly okay. And sometimes we have eligibility requirements in order to award points, and there is an eligibility requirement here, and I'll let you read through all of that. Again, there's a little bit down at the very bottom of these scoring notes about converting, or those students who converted to thousands. But as Vicky indicated, we don't think that's a good idea. Beautiful. Oh, and there's a partial credit table here once again, and you can again download this problem from AP Central and read through that and make sense of this partial credit. Let's take a look at part 3 here. This is a good one, good problem. It says, let's let A represent the estimate of the total number of plays for this song in thousands, A sub t. And we know A sub 1.5 because we found that, and we want to know, or we want to show that that's less than D of 1.5. Okay, it's easy, I think, for me to show that if I can look at this graph here on my TI-Nspire calculator screen illustration. It's kind of hard to see on the screen, but this blue curve right there, that's a graph of the quadratic, D of t. And the green curve is actually a straight line. That's a graph of the secant line. Well, the secant line is always below the graph of D of t, and the reason is because D is always concave down. How do you know that? Well, this is a quadratic, but the coefficient on x squared is negative. So we know that this has to be concave down, and we know that every secant line is below the curve. Therefore, that estimate A sub t has to be less than d of t for all values of t on the interval 0 to 4, and in particular, A sub 1.5 is less than d of 1.5. Now, I don't know what d of 1.5 is. I didn't calculate that, but I know that my estimate is below it. I think that's a good visualization. That helps me. I think that helps students too. I think we recognize that this curve is concave down. We know the secant line must be below it. I can see that those estimates are below the curve. Good. And there was one more, pardon me, there's the model solution. 1 point for that explanation. Very similar to what I did. I maybe parsed it out a little bit, but very similar to what I did. So they get the point if they recognize that the graph of D is concave down, or that the rate of change of D is decreasing. To me, that's a little bit more difficult to recognize, to convey, but that's okay. Some students could do that. And they must have some sort of reference to that secant line. Good. Part C. Okay, now I attacked this a little bit differently here. Okay. So the quadratic function has exactly one absolute maximum or minimum. Okay. That minimum and maximum can be used to determine the domain restriction for D, and let's figure out what that domain restriction might be. I'm paraphrasing here. Let me think about this a little bit. Well, let's see. We know that this graph is that of a parabola. We know from a minute ago that it's concave down. So we know that it must have an absolute maximum. So we know that the domain here, t cannot go beyond that value at which that maximum occurs because, well, then the graph would be decreasing and D is accumulating the total number of plays of this song. So it can't be going down. So I found the maximum of that function D, and I did it graphically. I did it on a calculator screen. There's a graph of that function D in kind of a nice window. And I found that the maximum occurs at t equal to 11, and the maximum is 40.1. And so that tells me that the domain here has got to be, well, less than or equal to 11. Now, you'll notice here that I said 0 to 11 because I was interpreting reading the problem, and that's when this musician first started using this app. It didn't make sense to me to think, well, could t be negative? But some students actually thought about that because t being negative is prior to when the musician started using the app, but people were still downloading songs. So students could have tried to analyze this function and looked at a left-hand endpoint that would have produced a negative value of t. I think, however, based on the context of this problem, explain how the minimum or the maximum is used to determine a boundary, a right-hand boundary for that domain. Well, we know here that beyond t equal to 11, D is decreasing. We know that D represents the total number of songs played, and so that can't happen. So t equal to 11 has got to be a right-hand boundary on the domain of this function. Long-winded way to get it, but at least I can see it visually. 1 point for the explanation, which is very similar to what we just did. There are some scoring notes here. A response that focuses on the left-hand endpoint of the domain is eligible. You'll notice that it's eligible. So that some students might quickly find that t equal to 11, but they also might take a look at, well, what's going on the left-hand side? where does that function d dip down below the x-axis for what value of t, and it will be negative. I think it was about a -7, -6.9. So, all right, to earn this point C, the total student must say something like, the number of plays cannot decrease, and the function model d decreases after that time at which it reaches its maximum value. So I get this visually. I think students have their calculator with them here. I think that provides a good visualization of how to answer this one. They do have to convey this in words. Readers, scorers, graders, we're looking for some sort of an explanation here. Beautiful. Tom, you want to try any technology on this one? Left you a lot to do there. I'm sorry.
Okay. Oh, that's fine, Steve. Sure.
Okay.
All right.
So while Tom's getting set up, that part of that question was very difficult for students. And Steve, I'm going to go back to something that you said early on when you were reading through the question. There's a
Yeah.
lot of words here,
Yeah,
but
man.
that idea of that this was an accumulation needed the students needed to think about that. And I think that was the hard part of this question, realizing that that absolute max on that function is where we have to draw the line, so to
Yeah.
speak.
Yeah.
Right. Okay. I think my 84 is probably showing. I hope so.
Yep.
It
Got it,
is.
Tom.
Great. Okay. I just wanted to look on the 84, some of the things that Steve actually illustrated on the Inspire, and go into a little bit more detail on how you could do that on the 84. And so I'm actually going to go to the stat editor and get my list editor there and put in those values that were given at the beginning of the problem. So the 3 time values, I think, were 0, 2, and 4. And then these will be thousands of downloads, I think. So
Yep.
we had 25 at 0, 30 at time t equal 2, and 34 at time equal 4. So we've got a small table of values, and I'm going to go ahead and do a quick plot of those. So I'm going to do the shift of y equals, get into my stat plot, and do plot 1 there. Turn that on. And I'm just going to do a scatter plot, and that's already highlighted. I think that's the default. It's lit up unless you've been using it for something else. And list 1 and L2 are already set up there. So I think this is ready to go. Let me go ahead and graph it. And I don't see much of anything. Well, it makes sense because I've got, I think here, this looks like maybe a zoom decimal window, even a zoom standard window. You'd be in kind of the same boat. The values are off the screen. So what I want to do is go to the zoom, and you'll use this a lot if you're doing statistical work on your 84. That zoom stat is going to pick out a nice window that'll fit all those data points. A nice form, and there we go. Okay, that looks very nice. So there's those 3 data points, and let's see, we might want to see now this problem was really specific. It wanted you to come up with 3 equations that would allow you to solve for those coefficients of that quadratic.
Right.
That said, Steve did kind of a check what happens if you did a quadratic regression and did that. Would that would be a means of coming up with those coefficients, even though it wouldn't satisfy the requirements of that problem. But we could do that as a check. And so let me go to the stat and go over to calculate. And you look down there at number 5, it says quad regression. And list 1, list 2 are already there. I would like it to not only calculate this, but I'd like to go ahead and store that in Y1. So where it says store regression equation, Let me go ahead and pull up the y variables, put in a y1 there, and then I'll arrow down to calculate. And when I hit enter, it gives me, well, this very general form of a quadratic. Why, that's this kind of the generic form, right? ax squared plus bx plus b. But it also tells me exactly what a, b, and c are. Those values look pretty familiar to me from what Steve had talked about. And what's moreover is if I go over to the y equals menu, I can see it's been automatically stored there. And so if I now graph, I'll not only have my scatter plot of the 3 points, but I've also got that quadratic that goes through those 3 points exactly. I think it's just a kind of a general word of warning. I mean, yes, you can use, especially if you know it's going to be a perfect fit, you might be tempted, well, why don't I just do a regression to come up with the curve that goes through the points? Just a caution there that for some regressions, as in particular the sine regression,
Yeah.
even if the graph, if you're given just a few points, like 5 points, let's say, that's a common setup for some of these AP precalculus problems where you're asked to find an exact model. Using that regression technique is likely not going to give you that exact model because it's using a technique that's iterative and is just not going to do the trick. For something like linear, if you know there is a perfect fit, actually you could use a regression to find it like we did here. But that's just to show us how to do a regression on this particular data. So I think I might, unless Vicky or Steve has something or something's come up in the chat that people would like to see, I can turn it back over to Steve because I know.
Tom, I've
Tom,
go ahead, Vicky. I'm sorry.
no, I was going to tell him, let's do the app on the simultaneous equation. Can we do that?
Sure. So
Yeah.
go to the apps. So poly simultaneous too.
Mm-hmm.
Okay. All right. I'm going to let you lead me through it, Vicky. If that's okay.
We're solving simultaneous equations. So
Okay.
the
Let's go
second
to
one,
number 2.
and Steve, you might have to help call out
Yep.
the
That's okay.
equations.
There was
So
actually
let's go
3
with the
equations.
fact. Okay, we can do 3 equations, or we can go with the fact that we were easily able to find the 25.
Right.
Okay.
C was
All right.
equal to 25. That would
Yeah.
be
So
very
let's
easy.
go with 2 equations,
Okay. 2
2
equations.
unknowns,
Unknown.
and basically it's next. Well, we could go to decimal if we
Oh,
wanted
next.
to make sure that we got our decimal values.
With float will work, right?
Yes, it should.
Okay.
Yes.
Radian degree doesn't
Well,
matter.
that doesn't matter.
Okay, so I'll just hit next.
Mm-hmm.
Okay.
Now we have to fill in those coefficients. So Steve, help us here because I don't have
Sure,
it
it
in
would
front of
be
me.
4x plus 2b, so 2y. Sorry, Tom.
That's all right. So we're using X and Y in place of A and B.
Mm-hmm.
Right, and that's equal to 5.
Okay.
Then the next one is 16x and a 4y and then a 9.
All right.
Now that's with a little bit of simplification. That's using c equal to 25, but
Right.
those are the 2 equations that we need to solve with 2 unknowns. Yep.
And now I think we're ready to solve. So I'm going to hit the that 5th key.
Right.
That's right under solve.
How about that?
And again, remembering that X is really playing the role of A for us, and Y is playing the role of B. That's exactly the values, actually in fraction form.
Yeah. So they would need to convert them to
They would need to
decimals,
convert. Yes, correct.
but
Let's see. There's a button here that
right
says
there.
fraction to
Yes. So
decimal.
click on
Let's
it.
press that. There we go.
How about that?
Okay. Good deal.
I think this is a beautiful app for
It sure
solving
is.
these systems, and kind of I, I would have my students practice it to make sure that they were pretty good at using it. They
Mhm.
do have to pay attention. Like when you were scrolling, going across, the all of our values were positive, but they would need to pay attention to putting in a negative if perhaps there was a negative value and stuff. So they have to pay attention to what they're entering, but it's a beautiful app.
Mhm. And it's closer to what was being asked for in this problem in terms
Hmm.
of we're actually coming up with equations that could
Yeah,
be used to solve
and
for this
knowing the way I go about things, I would probably do this first and then
Mhm.
do the regression to kind of as a double. I'd let the regression be my double check, to be honest with you.
Exactly, and that's I completely agree. Yeah, I think that regression's kind of a check. Is that really making sense? And
Hmm.
yeah, yeah, good deal. Okay,
Very cool.
all right. Well, Steve, I know you've got another
All
good
right,
problem to
we've
look
got
at.
one more
Want to
here.
share? And-
Okay, I like this problem. It deals with Burmese pythons down here in Southwest
Y'all
Florida.
got some of those down there?
We do indeed have some of those down here. Yes, I'd say about 5 to 8 years ago, they started a 1 day a year where they would let people go out and hunt and try to catch the pythons, and they would get paid for the number and the size of the pythons. But now I think you can do it all year round because there's so many of them. I'm not sure. Anyway, this table shows estimates. They don't know how many, of course, but these are estimates of the number of Burmese pythons in Florida by year. And this is actually pretty close. It's not quite exact, but it is actually pretty close to what's going on down here. So in part A, let's let T be the number of years since 2000. So 2001 will correspond to T equal 1. And the very first thing I want to do is to construct a scatter plot of this data. I want to get some idea of being able to model this. What kind of a function could I use? Is it quadratic? Is it cubic? Is it exponential? Is it sinusoidal? So anyway, I got a scatter plot. I want to get a scatter plot, and I want to determine if this model appears to be logarithmic. So, okay, I'm going to use the TI-Nspire once again. It's made to do something like this. In a lists and spreadsheet page, I've created two columns, one called year and one called pythons. I've shown you the first 5 rows of that data, but of course it extends down here all the way to 2025. And then on the right-hand side, I've got a scatter plot of that data, which is extremely quick, very easy to do, graphical actually, to put the year on the horizontal axis and pythons on the vertical axis. The Nspire recognizes the current variables in this problem and allows you to pick them very easily. And as I look at that scatter plot, I think, you know what? It does look like it might fit a logarithmic model. Okay, one might argue quadratic, but I don't know what's going on there beyond 2025. It doesn't seem likely that the number of pythons is going to decrease if they've hit some sort of maximum. Although, before I decide that it is logarithmic, I also just want to think about, physically, I mean, what's going on here. The pythons, the number of pythons expanded very rapidly here in the first few years. I think their food supply was great. And so they were able to grow and expand. Now there's so many of them. The food supply is limited a little bit. There are rumors that the alligators are now learning how to combat these Burmese pythons. And so they're able to kill some of them off. So they are sort of leveling off here. This seems very reasonable. It seems like a pretty good model. So I'm going to answer B and C here all in one motion here. It says, use the regression to find the logarithmic model in that form, A plus B times the log of T. And I want to add that graph of that logarithmic regression to my scatter plot. Well, there it is. It's very easy on the Nspire to find that regression model. And by the way, Tom, you were able to show how to store that regression equation on the 84. The Inspire also stores that regression equation in a special variable. It also stores the residuals so that I can use those to create a residual plot, and stores the constants A and B in variables so that if I wanted to use them, I could in some special way. So you know what? My model seems pretty darn good. We don't expect anything to be exact like this, but that regression model, that logarithmic regression, sure appears to fit that data very well.
Just a real quick note there, Steve, maybe you already noted that is,
Yes.
yeah, I think there was an ln missing from that, the bottom of that previous.
Oh, right here. I apologize.
The
Right
P,
here.
Oh,
yeah,
yeah.
and I'm sorry I didn't catch that earlier. So
Yep. There's a log T in there.
could
Thank
be
you.
ln T. Yeah, there
Yep.
we go.
Thank you. Yep. Cool. Okay. I think I have a part D here. It says to use the model to predict the number of Burmese pythons in 2026. You know, when we do regression analysis, there is always danger of trying to predict, use the model to predict what's going on outside your range of data. But that's what we often do. We expect circumstances to remain the same. And so you can see this sort of variable that the regression equation is stored in, and I evaluated it at 26. So my model predicts that there will be approximately 199,000, holy Toledo, Burmese pythons in 2026. Wow.
And Steve, you could have also used the function that it was stored under if they wanted to just pull it up instead, right?
Well, I think Vicky helped me on this one. Tom, you'll Curtis, on the Inspire. I don't know if it stores it under any specific function name. I think it stores it under this sort of function name, stat.regression equation.
Okay, I think you can on purpose store it somewhere.
Store it somewhere in like an
Yeah,
F1 or
like
F2.
F1. Yeah, yeah.
Right.
Okay.
You can on Inspire. Oh,
But this is done automatically, right, Curtis?
right. The stat not regression is done automatically,
Okay.
and you can choose from the calculator if you do the regression on on a calculator page. You can choose where to store it
Oh,
um,
right. Okay.
as well, and it's part of the wizard is to
Okay.
store it in
Okay.
like a function or whatever. Um,
So I did this.
I'll have to comment again in just a second to remind myself whether you can do that from the statistics and from the data and stats page or not.
Okay.
Um,
So I did
the
this,
wizard
Vicky. I
pops up.
found that regression equation on the data and stats on
Okay.
this page.
Yeah, I
Okay.
typically go to a calculator page or go back to I get lazy and do it in the table in one of
Yeah,
the
if you do
cells
it in
Oh,
in
the
the
yeah.
table,
table.
you get the same option.
Yeah.
Okay.
If you do it in the table, you also get the wizard. But I
Okay.
don't think you get the wizard in the data and
In the
statistics
yeah.
page. But I'm gonna validate that shortly.
Okay.
Okay. So one of the things in pre-calculus that we're often asked with regression models, polynomial regression, linear regression, exponential regression, logarithmic regression, we're often asked about residuals. And so I'm going to start out by simply finding the residual associated with t=9, and then I'm going to analyze these residuals. So we're going to use this to determine if the predicted value for t=9 is less than or greater than the observed value for t=9. Loads of different ways to do this. I've kind of done it mathematically on the left-hand screen, and I'm doing it visually on the right-hand screen. Let me see if I can decipher all of this. So one of the things I did is the TI-Nspire stores all the residuals in that list. I think it's stat.resid. So I could look at that list and sort of pick out the residual that I need. You know, it's the one that goes along with t=9. So it's the ninth one in that list. And so by typing this one, I have asked for the ninth value in that residual list. And it's a 16.7512. Now, just to double check that, because I couldn't see it in the list above, this was my list containing the number of pythons. So I took the 9th value in that list and I subtracted off the value of the regression equation at t equal 9. That's actually the formula for the 9th residual. It is yi minus yi hat. Y9, y sub 9 minus y sub 9 hat.
And most,
That
if we do have students on here, most of you have probably heard actual minus predicted, which is that's exactly what Steve's giving you and showing you.
So it's positive. This value is positive. So that means that the actual must be greater than the predicted. Now you can also see this visually. I don't know if you can see this on the screen, but there's the actual coordinate that corresponds to t equal 9. And you can see that that's above the graph of that regression equation. So I've done it mathematically on the left-hand side, numerically, and I can see that visually on the right-hand side. That's kind of cool. All right, now one more thing here. In statistics, one of the first things we do once we construct a regression equation, all right, we're going to look at things like R squared, and we're going to look at whether or not the coefficients are significant. But to decide whether or not a model is appropriate, we often look at a residual plot. A residual plot is a plot of the residuals versus not the predicted value, but the observed value here, the x value. And so I've got a residual plot there, and we're hoping that there is no discernible pattern. If there is a pattern of any kind there, like all of the residuals were positive, or you could see a quadratic equation, sort of following a quadratic curve there. Or if you could see down the left-hand side, the residuals are clumped together, but as you move to the right, they expand. If there is some sort of pattern there, that's evidence to suggest that the model is inappropriate. It doesn't necessarily tell you what the right model is or what a different model is, but it tells you that something's wrong. We might also look at this residual plot and see an outlier, an observation that's very, very far away from the rest. That's an indication that you might want to go back and check your data or check the model. Something could be wrong. Well, after all of that, as I look at that residual plot, I don't see any pattern there. I don't see any outliers there. To me, there's no evidence to suggest that the logarithmic model is inappropriate. And I think Vicky helped me on this one, but I think students would be expected to provide some sort of explanation, something in words about this. If the question says use the residual plot to determine if there's any evidence, I hope that they would come back with a sentence, something like that.
Well, it's probably going to be a multiple choice question, but they're going to have to read very carefully because they'll say something like, there is evidence that it
There is
is
no evidence.
appropriate.
Yeah.
Yeah, there isn't. Yes, it's like there's 4 combinations here.
Yes.
And so
yes.
they'll have all of them as the things. Okay, before you leave the screen,
Yes.
kind of eyeball the t equals 9. We've got 8 on the axis, year 8. So we
Yes.
go over slightly to 9
Yes.
and look at that point way up high, and it's around 16. And
Yep.
that's indicating that residual value that we calculated a few minutes ago. So that's sort of a different visual to confirm that that it's a positive residual value. So I mean, I just love how this kind of
This
all
work.
weaves together and everything.
Vicky, Tom, I think if I wanted to, I did not do this, but I think if I wanted to, I could trace this graph and
I
I
think
could trace along the points. And if I
Yep.
got to that one, it would give me the coordinates.
I think so.
Yeah. So that would be kind of cool too. Okay, Tom.
Okay.
A little
Yeah,
bit with the 84.
sure. Sounds great.
Okay. There you go.
Okay. All right. And let me see if I can pull up my 84 again. Hopefully you can see that okay.
We've got it.
Great. Okay. I'm going to go back to the stat editor here, and I went ahead and took the liberty of entering uh, the number of pythons. Okay,
Uh-huh.
that's varied, from year to year. But I didn't enter the year number, and Steve said he wanted years since 2000.
Right.
That turns out to be just the numbers 1 through 25. Now I could just type those in 1 through 25, but when you have regularly spaced data, sometimes you can make use of a sequence command. I just wanted to illustrate that quickly. So I'm going to go, let me quit from here, and now I'm going to go to the list, to operators, and number 5 there is that sequence function. And what I've already entered here, you put in the expression. This could have been cleared out, but the variable's in, the expression is in. I'm going to start it at 1, end it at 25, and just step by 1 each time. And let's go ahead and then paste that. Excuse me. And there it is on the home screen. And then we're going to store that in L1. Great. And not only is it here on the shown, we can see those numbers 1 through, well, I'd have to scroll to see the whole list. But if I go back to my stat editor, L1 has the numbers 1 through 25 in it. And so now I'm ready to go ahead and plot this. So let me go to stat plot. Number 1, let's turn it on. And let's graph it. Of
Oops.
course, not going to see much. So let's go ahead, go to the zoom, go down to zoom stat. And there we get a very nice plot. However, I would draw a note to the y-axis here. It just looks like it's bold with no tick marks. Well, that's because there's a whole lot of tick marks. Because the range here on the y-axis is really quite large. So what I want to do is go back to Window, and you see the X scale is 1. That works just fine. I might want to change my Y scale, given that large difference between Y max and Y min. I'll set it to equal to what Steve used, I think, which was 60. And if we graph again, each one of these hash marks on the y-axis is 60. Okay, so we wanted to do a logarithmic regression. Let's go back to stat. We'll calculate. Let's see. Oh, there it is at the bottom. ln reg, logarithmic regression. Looks good. List 1 and list 2. Let's store our regression equation in Y1 and calculate it. We can see that there's the generic form, a plus b ln of x, and it gives me my a and b coefficients there. But again, what's nice is if we go over to y equals, it's been stored there. We can see actually to much more accuracy in those coefficients. And then we could graph, and we can see how nice a fit it is. Now, if I turn on trace, let's see, this is actually tracing the scatter plot. So if I increment, it's going to jump from point to point. And so we could go, for example, for us, x equal 9 means 2009, okay? There we go. There's that plot. And we can see that that point is above the prediction curve, okay? If I hit an up or down arrow on my trace, it shows me the value oh, I wanted to be on the prediction curve. I wanted to be at x equal 9. So let me just type in 9. And now that's the actual predicted value there at 9. Let's see, I think one of Steve's other questions was actually extrapolating, going beyond the data for a predicted value at 26. Well, let me just type in 26 for x. Boom, there we go. We're predict out there. So it's very nice there. Let's see, I think the other thing Steve looked at was residuals. Again, very handy, easy to do. Let's go back to the stat editor. Now, we'll take a little bit of a shortcut here. What I often like to do is I'll go over to, well, I'll show you because it's actually quite easy to do. I'm going to make L3 equal to Y1 of L1. So that gives me a list of my predicted values.
Okay.
And so now I can make L4 equal to L2 minus L3. And those are my residuals. In each case, it's taking the actual value minus the predicted value. If you just read across, you can see those differences. There is a shortcut to this. I'll show you how to do it in L5. If I go to L5, I can make it equal to, well, let's go to the lists. Notice number 7 down there says residual. So we could go ahead and say, just automatically give us the residuals. And you can see L4 and L5 match up exactly. Okay. I often like to do the L3 and L4, just get it in my students' head, remind them that's what those residuals are. It's always the actual minus predicted. Go ahead, Curtis.
Well, I think that's a really good point, Tom, that you're making, that you know, those are the actual minus the predicted values, and doing that demonstration is really a good one. I think it's also important to just remember that that list resid is filled with the most recent set of residuals. It is calculated automatically. And it can get, you know, it can get a little hairy if you've done a few regressions and you forget whether you've actually calculated the regression or not, and whether those residuals are really the residuals from the most recent one. So, you know, always make sure that you've carried out that regression first before relying upon that list resid as sort of the automatic calculation of those. I also was going to just comment back that I did confirm that Steve's experience of not being able to store that automatically on the data and statistics page is true. You can't store a regression equation from the data and statistics page directly. You've got to either do it in the lists or in the lists and spreadsheets page, or the calculator page, as Vicky kind of pointed out earlier. So,
Thanks.
Yeah, and maybe just one final show here is I'll go to the stat plot and go to plot 1. I'm going to leave it on, but I'm going to change it to a residual plot. So I'm just going to change my Y list from L2 to L5. That's where we had the residuals. Okay. And let me go ahead and do a zoom stat. And hopefully we'll get a very nice residual plot. The one thing I forgot to turn off was the Y1.
Yeah.
And so I still have that graph. You're just seeing a little bit of it there. But this is that residual plot. If we did a trace of the residual plot, we could go over to, again, 9. and see that large positive value. Yeah, that's actually it's interesting that particular value, Steve, was the largest, had the largest individual of
Yeah.
all the data. Yeah.
And Tom, when you were in the setting up your stat plot,
Mm-hmm.
if you you could also just put resid in there for
Right.
Quite.
I mean, so,
Good point. Good point.
but
Without
let's go.
even
Yeah,
not even making one of the lists equal to
right.
resid, you
But go
could
back to what Curtis said. You better have run the
You better be
regression
careful
before you did.
because that
you know which
regression is
residuals in there.
calculated.
Right.
Yeah.
Yeah.
Right.
All right.
Right.
I'll stop the share there. And
So, Tom, Vicky, one other question that we'll leave as an open question as we close for tonight. You know, part A in that problem about Python said, you know, use a scatter plot or construct a scatter plot, and does in a logarithmic regression or logarithmic model seem appropriate? If the problem did not say construct a scatter plot and you weren't going to construct a scatter plot, how would you try to convince me that a logarithmic model is appropriate? And we'll leave that as an open question.
It's a great question, Steve.
In the
Really,
pre-calculus way of doing things, how would you do that?
yeah, no, that's a great question to end on. Just one bit of housekeeping. I put my email, curtis@ti.com. So if you're looking for that certificate, you can certainly reach out to me. We are signing off for the end of 2025. So I hope everyone has a wonderful rest of November and into December, holidays and all. Very excited to have that time coming up, and then we'll be back on here in January. The date of that first session in January is on January 29th, as I have it recorded right now, which I believe is a new functions from old. We're going to be starting with transformations in the beginning of the new year. So look forward to that session. We'll be, of course, marking this on the Facebook page and also in emails and things from the Texas Instruments email campaigns. So enjoyed it thoroughly. Thanks, guys. It was a great session, and we'll look forward to seeing you guys next year.
Thanks, Curtis.